topic of our experiment is force vibration with a single degree of freedom. Okay, force vibration means when the dynamic system is subject to steady state harmonic excitation, it is forced to vibrate at some frequency as that of the excitation. Now we will explain about our objective. Our objective is first to determine natural frequency by using variable oscillating mass for underdamped system. Second one is to compare between experimental and theoretical calculation value of natural frequency. And the third one is to relate the natural frequency with mass.
Boleh.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hanif. My entry number MK10089. Okay, firstly, I want to show apparatus force vibration. Okay, first we use Daisy Lab. This is a Daisy Lab, and then this is a tachometer. Tachometer is an instrument measuring the rotation speed of shaft of orbis, as in a motor or other machine. Okay. Okay. This is a AC motor. AC function for AC motor is it commonly consists of two basic parts: an offset stationary stator having coil supply which alternating current to produce a rotating magnetic field. Okay. This is a motor controller. Motor controller is a device or group of service that serve to govern in some predetermined manner the performance of an electric motor. Okay. And lastly, this is a transducer. Function for transducer device that convert is a signal in one form of energy to other form of energy. And lastly, we use three type of weight. 500 gram, 300 gram, and lastly 100 gram. Okay.
My name is
Okay.
Yusuf from the Foundation. Today I will present about the apparatus setup. Firstly, when the open computer, next
Software.
then DAQ connect to the computer by using Daisy Lab. Next, connect transducer at the DAQ. If transducer at channel 0, must at DAQ
0.
channel 0. Setup the as model for experiment. Then setup motor and adjust following
Wait.
the experiment. Set up the mass at the motor. We use we using three type for mesh, 100, 300, and 500 gram. Set up LVDT sensor and determine position in parallel. For tachometer, determine the target
Laser target.
at the plate disc.
Dah 2 minit.
For AC servo motor, connect the cable at the motor, then on the switch. Adjust the control speed following the experiment. And then collect from the data at DesiLab.
Thank you.
Thank you.
Hello, my name is Azira binti Hazmi and I will explain about data acquisition and DesiLab. Firstly, we will open the AQ. We choose data neighborhood and then create new file. We choose echo signal and analog input and choose voltage. There is 2 signal. We click 2 and then create enter name our file as group 3A2. Finish. And then we exchange to continuous sample. We run the data and then click save. Okay, next we will open the DesiLab. Okay, for DesiLab, we do synchronization first to connect data from the AQ to DesiLab. After that, we open our save file. Okay, we change the task data, delete the module and create new. The data is from the data acquisition. Yeah, and then we click to channel and then link it with scaling. Okay, from the first link, connect it to the original of YT chart, and the second one we connect to path analysis. Path analysis is used to read the data from tachometer, and then we do again synchronization. Okay, and then for scaling we use offset adjustment so that we didn't do the sensitivity. Okay, this is for raw data, the original frequency, and then for filter we read the data frequency from the tachometer. The value from tachometer is 8, we set as low pass. The filter order is set as 8. Okay, for data window, we use Henning. The block size is 4096. After that, for frequency control. Frequency control being filtered to read the filtered displacement. We use again low pass. The time window we use is Henning and using the same block size with the data window before. Okay, for frequency channel, we use right window to read the data from the FFT. Okay. This is our layout. The system frequency that we use using Henning, the motor speed from the tachometer, the raw data, the original before it being fitted, and then for displacement data, the first one is original frequency and the second one is fitted displacement. That's all.
Assalamualaikum. I'm Nazura binti Razali. I will present about result from my experiment. Okay. In this whiteboard is our result and calculation. Firstly, okay, for sample, I just pick only one weight, which is mass equal to 100. Okay. First, I calculate theoretical data for theoretical. Okay. First, mass of bean, I get this one, and then mass of motor, I get 1828.5 gram, and then length of bean, this one, okay, and then thickness of bean and width of the bean. Okay, I find this to find the theoretical. Okay, firstly, okay, I calculate total of mass. Total of mass include mass of the weight, and then mass of the motor, and then mass of the bean. Mass of the weight 100, and then mass of bean this, and then this. Okay, then I get total of mass 3.011 kg. Must be in SI unit. Okay, and then to find natural frequency, omega equal to K over M. M, this one, I get it, and then how to find K? Okay, K stiffness of beam. Okay, K equal to 192 EI over L cube. Okay, this formula for feet support beam. Okay, and then I put the value E, I get for the moment of inertia. Stop. Of inertia. I use this one formula because beam rectangular. Rectangular. How to find moment of inertia? Use this equation. Okay. Then put the value. Then I get it. Okay. Then calculate the stiffness of beam. Put the value untuk for Young modulus elasticity, moment of inertia, and length of beam. Then I calculate, I get 7929.6 Newton per meter. Okay. To find the natural frequency, omega naught equal to third K over M. K, this one, M, this one. And that form, I get 1.32 radian per second for theoretical. Okay, this one. Then I repeat the same step to mass 300. And then I get theoretical value 49.69. And finally, I repeat again using weight 500. And then I get theoretical 6.283. Okay, for experimental natural frequency, this is our formula. Omega naught equal to 2 pi f. For f, I get from the data from the experiment. Okay, then I put the value, then I get 52.15. Okay, repeat the same for mass 300 and 500. Okay. So, my objective is to determine the natural frequency by using variable oscillating mass for under damped system. So, and then to compare the experimental and theoretical calculation value of natural frequency. That's why I calculate percentage error. Okay, this is formula for percentage error. Natural frequency theory minus natural frequency for experiment divide natural frequency for theory and times 100% to find the percentage. Okay, then I put the value, this one for mass 100 gram. Okay, I get 1.56% for true error. Okay, for my second objective, I want to relate the natural frequency and mass. Okay, I use this equation, omega naught equal to K over M. Okay, what do we know? Okay, when mass increase, natural frequency will decrease because natural frequency is inversely proportional to the mass. That's why mass increase, natural frequency decrease. Okay, if we decrease mass, natural frequency will be increased. So from the true error, okay, we prove that objective of the experiment achieved. Okay, thank you. That's all from me.